integration, right?
Yeah, they're mostly full integrations.
Because we did D flip-flops, JK flip-flops, what would be the one chip, if any, that we did that would be medium scale integration?
93?
The 93, because it combined multiple things into it.
Yeah.
We use that 93 on activity 322. We also use that 93 on the now serving activity. So we did a little bit with medium scale integration, or at least more pins. Medium scale typically means that you're using 10 or more pins for that one process, whereas small scale is that under 10. So that's why your JK has a J, a K, a clock, a preset, a clear, a Q, a not Q. So we're using 7 pins there. It's still small scale integration. This PowerPoint goes ahead and talks about 163s and 193s. So looking at this real quick, we can see that 163s are going to be up counters. They're a 4-bit up counter. So it would be the highest number we could count with a 163. 15. 4 bits. So we have our 1s, 2s, 4s, and 8s would give us 15. The 163 or the 193. So we had the 93 before, and I know when I was helping someone with the 93, I accidentally typed in 193 because I knew it was coming up. The 193 is a 4-bit up-down, so it can go either up or down depending on the situation that we want. So we've been doing all different types of counters with Ds, JKs, and we did use the 93 a little bit. This presentation is going to talk about the 163 and 193. So looking at the 163, the emblem on the left, or the image on the left, is what it's going to go ahead and look like in multisim. The one on the right is the layout on the actual chip. So if we look in our chip bin,
Do we have any 163?
in the chip bin, we have a slot for 163s and 193s. We do also have a slot for 93s, but though we have all 3 of those in our chip bin depending on the application that we need to use those for. On the right, like I said, is that pinout of what the chip actually looks like if you hook up wires to it. Yes, Brandon?
Is there a preset?
So when we're looking at that's a real quick thing that you notice that we don't have a preset.
There's no load. We don't need one, do we?
So load is going to load whatever we have waiting. So we're getting a little bit ahead of ourselves. But what this is going to do is we've got enables here. So what type of trigger are those enables? Positive level. So as long as we have positive going into those, we're enabling our device. We have our clock down here, right? And this only counts up, so as soon as we hook up that clock, it just starts counting up. The A, B, C, D on the left-hand side are kind of like your presets and clears that you used before. So we could go ahead and say that we want our count to start at 2. If we wanted to start at 2, we'd go ahead and type A, which is our least significant bit, to ground. We'd type B to our power, C to ground, D to ground. So then we're telling it we want it to start the count at 2, and then we detect what we want to over here on our outputs, and fire load. What load is going to do is it's going to take whatever's setting up here on the left-hand ABCD and load it into the circuit. So if I set a 2 to 13 counter, we detect over here, fire to load. Clear is going to work just like clear before, so clear is going to reset to 0, even if you have something waiting up on your ABCD. So we have a little bit of options there. They talk about it a little bit there, that same idea that A is the least significant bit, QA is the least significant bit. Hopefully you recognize what LSB and MSB mean by now. Hopefully. There's the two enables that we just talked about. Load we talked about. Clear we talked about. Clock. RCO we didn't talk about. That's ripple carryout. That's an output. That'd be if we were going to another chip and we want to overflow. So if we're counting in hexadecimal and we have another hexadecimal 7-seg next to it that this is overflowing into once we reach 15, when we hit that 16, it'd give us a 1 in the next hexadecimal, and this hexadecimal would reset back to 0, right? So that's where that ripple carryout is being used.
Will we use them?
No, not in this class. Notice that load and clear are what type of trigger?
Negative.
Negative,
Add.
negative,
Ground.
negative level.
Level.
So as soon as they get it, or as long as they have a negative to them, they're going to be activated. So we would use what type of a gate when we're detecting our upper limit, bringing it around to load?
Invert man.
4-input NAND would probably be what we'd end up using. That way it goes ahead and outputs that negative to load. Because we can take those 4 inputs off of QA, QB, QC, QD and invert them as need be to detect our output. Right here's what it would look like if we did not have this chip and you had to use your JKs and AOI logic. They always like to throw this in there to go, hey, aren't you glad we're teaching you about this?
After we've already learned all this.
This is going through timing diagram. I think we understand how JKs work. I think that there's enough lines here that if I were trying to explain it, we'd run out of class time.
And
I
we
think
get
we
all
can
get
learn it.
messages.
You said we need to learn all the content, which is why we learned the original one.
Looking up here, they went ahead and built their circuit. Notice that they have down here that oscilloscope reading, that clock. Every time it clocks, it ripples along or triggers along all the way up until we're at all of them high, which would go ahead and be our 15. And then we have that ripple carryout that comes in next once all of them go high, saying that it'd ripple on over. Right here, they put in reset logic for us. So, what are they detecting to do the reset? So they're detecting,
11.
D is the most significant bit.
11. 11.
So 8 plus
13.
4,
13.
13. So they're detecting 13, which would be which letter?
Oh,
D.
D. So when we look down below, notice that we see that it goes up to D, right?
yeah.
Just kind of keep that in your mind for a little bit. Then notice up here that they've gone ahead and powered A and B. That means that they're going to reset to what?
3.
3. 1 plus 3. So it goes D, 3, 4, 5, or we can see it here, 3, 4, 5, 6, 7, 8, 9, A, B, C, D. What's different about that and what we did with JKs and D flip-flops?
You only go one ahead with the JK and D flip-flop. This is the exact.
Right, so this one on the 163,
Doesn't have the ripple effect.
we actually go ahead and set it to detect what we want to end at. The reason why is because with the JKs and D flip-flops, they were asynchronous, meaning that as soon as they received that signal, they went ahead and reset. This is an synchronous counter. What that means is it only will load or clear when the clock fires. So that load and clear doesn't do any good until the clock fires, which means that the clock fires and changes up to that 13 or that D, and it's saying, hey, reset, 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 but it doesn't listen to it until next time that clock fires. When that clock fires, it goes, oh, okay, I'm supposed to reset to whatever's loaded. So it's a little different technique than we went ahead and did with JKs or Ds. Maybe I should back up just a little bit and look at one thing here. So when they were introducing it to us, notice right there it said synchronous load, synchronous clear. When we get to this 193, I was noticing that it tells us that they're asynchronous load and asynchronous clear, which means that they're going to be like,
Ripples, you have to go one ahead. Yeah.
they're not going to be ripple, ripple's dealing with the clock, but they're going to be like JKs and Ds, where you go one ahead.
Why is that?
So the 163 is the only oddball one that we've learned.
Yeah.
I would just not use 163s.
193 is the way to go.
Well, what's the advantage to a 193 over the 163 that we've already kind of
Get down
discussed?
count.
It can down count. So the 193 will do your up count like the 163. It will also do your down count. So what that means for us is not only do we have our carry out, we also have borrow out. Because if we're down counting and we're going 17, 16, 15, we need to go ahead and pull away from the previous chip to go ahead and down count. We don't use two hexadecimals, but we have that carry out. We have QA, QB, QC, QD. We have A, B, C, D up here for load. Notice that load is what type of trigger?
Negative.
Negative level, whereas clear is positive level. So depending on what we're looking at there, one's negative, one's positive, which is different than the 163. The reason usually that they do that is because think of all of that logic that they're trying to cram on that one little TTL chip, right? So they're trying to find paths in there to connect the transistors, and sometimes it's one way, sometimes it's the other to get the solution to fit on the package that they're provided with. We work with what they give us. Then notice that they have these up-down counters, right?
Yeah.
So whichever one we connect the clock to is which way it's going to count. They are what type of trigger on the up and down counters?
Positive.
Positive. Rising edge. So on that rising edge of the clock, it's going to trigger that count. We learned that these are asynchronous, which means what again?
You have to get one out.
You have to go one ahead on your count range. So right here it talks to the same stuff we just did before. We already talked about all of that. That's what it'd look like if we didn't have it all in that one package. Yes.
Why is some stuff asynchronous and other stuff? Is there like a reason something could be asynchronous? Like a reason it should be over regular synchronous?
So synchronous would be if you only want things to happen when the clock occurs. So if your clock, for example, is tied to an alarm of some sort, you don't want to recognize the situation until that alarm cycles through its paces. Maybe there's other stuff going on. As far as counting, there's not really an advantage to one or the other. These are just the chips that we're given. A lot of it comes down to what they can get to work on that package. Other questions?
What's kryptonite?
I use the 193s. This is another one of those that goes through a really big, fancy oscilloscope reading that we don't need. This one goes ahead and shows us that counting. So notice that they've tied their clock to which type of count? So this is going to be an up counter for us. We can see that they tied their down counter to what?
Power.
Power. That way it doesn't accidentally float. We don't want to leave that pin floating for us. So what they're doing here is they haven't hooked anything else up. So it's just counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 0, 1, 2, and going through that cycle again. It is going ahead and firing the carry out, which is going to go ahead and carry out to the next chip if we had one. Here what they do? What's different?
It's a down count.
It's a down counter. They just flipped where that clock runs to, so that we now have a down counter. And notice now that we're activating the borrow outs every time that it hits the end of the count. And right here they've gone ahead and set up a count range. So first of all, what type of counter is it, up or down? Down counter, because clock is tied to the down. So if we look now up at their reset logic, they're detecting the most significant bit off, which is the 8's off, the 4's off, the 2 is on, the 1 is off. So what is our end number going to be?
1.
We're detecting a 2.
It'll be 1.
3, I heard it over here because it's a down counter, so we're counting 7, 6, 5, 4, 3. As soon as it detects that 2, because it's asynchronous, it resets. So our last number we'd see would be a 3.
So we 12 to 3.
When we look up here, it's going ahead and most significant bit is on, 8's on, 4 is on, 2 is off, 1 is on. So we've got 8 plus 4 is 12 plus 1 is 13.
So when you're reading 12 to 3, 12 to 2.
So it's going to be 13 to 3. Because that 2, it sees and resets right away.
Oh yeah.
So if we look up there, it's actually going DCB A9876543. They don't show that little bit where it fires. I don't see it firing that
It's all
2
red,
for
so
us.
there's a lot.
Because it would ideally fire that 2 for just a little bit if we zoomed in. It's too fast for us to see, and it resets back to that D.
What's the VO and CO?
Why is the
VO and CO. Borrow out is going to go ahead and, like I said, if we had two hexadecimals set up next to each other, when we're counting down, it's going to borrow away from the other one, kind of like you do in addition or subtraction, where you're borrowing. Whereas carryout or carryover would be like addition, where you're carrying it onto the next bit. We will not use those unless you use it on a later project where you decide that this is the best solution for it. As far as why the computer is like that, what I've got is I've got my screen in presentation mode.
Because you
So
have dual monitors.
right here is actually the side and the notes and all of that, which I used, if you didn't notice, while I was presenting. Every time I ran up here real quick, read the notes, ran back there and told you what the notes said. That's how I knew exactly what I was talking about.
Okay.
And then I have my second monitor set up as the projector, and I set the thing that takes over the computers as to look at the second monitor. The only issue is the projector it recognizes as a lower resolution, so it goes ahead and gives you guys a lower resolution and puts the gray around it.
So you read the notes at the bottom right now.
Yeah, every time in between I ran up here and read them and then ran back there, so I knew what I was talking about. I suppose I can leave the video recording while I go ahead and talk about the next part.
You're recording this entire time?
Yes. Hopefully. I don't know. So if I look at the assignments, so if I go into 3.3, that was the PowerPoint point for 3.3.2, we've got two assignments that go along with it. We've got 3.3.2 and we've got 3.3.3. One of them is going to deal with the 163. One of them is going to deal with the 193. So if I go ahead and open up the 3.3.2 and I put it on the screen that you guys can see. So right here gives me an introduction, says that we're going to go ahead and build with the 163 chip. Goes ahead and says below are two MSI synchronous counters created in design mode of the CDS. They are the 163 up counter with synchronous load and the 193 up down counter with asynchronous load. So they're showing us the difference between those two. Each of the MSI counters has a corresponding representation on the PLD mode, which we haven't really done anything with PLD. And it's just going through and talking about it. The next activity, if I were to look at that as well, it does want you to do some stuff with PLD, but we'll go ahead and get to that eventually. So 3.3.3 says, okay, right here is a 13 to 6 with the 193 MSI. And it says that we're going to modify it so it's a 6 to 13 and talks through all of that. So should we kind of omit these assignments and jump into me giving you your own type of thing? So both of these are counters, right? The 163 can only go up. So I'm going to kind of take something like they have, and we're all going to start with the same assignment. That way we can help each other. Then we might move into an individual after that, kind of like we did before. But if we all started with a 3 to 14 up counter in the 163, then with the 193, if we made that a 14 to 3 down counter, would that sound fair for us to do the first two assignments?
Yeah.
Then what we'll do as the third assignment tied in with this is we'll go ahead and take that same number that you're probably getting tired of by now, the individual one, and you'll get to choose how you build it. Most likely you'll all go with the 193, but that's what we'll be working through. That'll probably plan on taking today and tomorrow, wrap up the week. Yes?
And is this supposed to be as easy as I think it is?
Yes. Okay, I'm going to go ahead and end the show. Maybe I should make sure no one has 3 to 14.
Yeah, Nick, good call. I got it.
Okay, so I'll have to give you a different one when we get to your individual.
Alright,
That's easy enough.
it shouldn't be too hard.
Nope, it's not.
Do you let go of our computer?
Get in there. In show.
Oh,